You know, most of the math we learn lives on a flat page, but the world we live in, it's definitely not flat. Today, we're going to make that leap. We're jumping into 3 dimensions, visualizing not just simple lines, but entire mathematical landscapes. I mean, really think about that for a second. We're taught to plot everything on a simple XY graph. But reality is, well, it's never that simple, is it? It's about time we broke out of flatland. All right, let's get into it. And like with anything new, the best way to start is to build on what we already understand. We're going to start with the basics. Oh yeah, you've seen this a million times. Y equals f of x. You plug in one number, your x, and boom, you get one number back, your y. It's simple. It's predictable. It gives you a nice clean line or a curve on a flat plane. It's our comfort zone. This right here, this is the question where our 2D world starts to fall apart. Because let's be honest, almost nothing in the real world depends on just one thing. The weather, the stock market, even the flight of a baseball. There are so many factors at play. Here's a perfect example. A savings account. How much money you end up with depends on 2 things, right? How much you put in to start, that's the principal, and how long you leave it in there, that's the time. Suddenly you have 2 inputs determining one single output. Our trusty old y equals f of x just can't handle it. So if we want to play in this new space, we need a new set of rules. It's time to properly define the world of multivariable functions. The big idea is actually pretty straightforward. Instead of just one input, we now have 2. We have an x and a y. We take this pair of numbers, we feed it into our function, and it spits out a single result, which we're going to call z. 2 inputs, 1 output. Now, to actually see this, we're going to need a 3D coordinate system. And there's a standard way of doing this, a convention called the right-hand system. You can do it with me. Point your index finger straight out. That's the positive x-axis. Now curl your middle finger out. That's the y-axis. Where does your thumb point? Straight up. That's the positive z-axis. It's just a simple trick to make sure we're all oriented the same way, looking at the same picture. And here it is. This is the giant leap. When we plot all of the possible points, every single x-y pair, and the z-value it creates, we don't get a flat line anymore. We get a surface, a whole landscape with hills and valleys and plains, all described by one single function. This image shows it so well. See that flat grid on the bottom? That's our xy plane. That's all of our possible inputs. The function then tells us, for every single one of those points, how high up to go. That's the z-value. And when you put all those points together, they form this beautiful, flowing surface. Okay, I know what you're probably thinking. That shape looks way more complicated than a simple curve. So how on earth do we analyze it? How do we understand what's going on without getting totally lost? Well, turns out we have some really clever tools for that. The first tool is actually beautifully simple. If you can't wrap your head around the whole thing at once, you just take a slice of it. We call this slice a trace. Imagine our 3D surface is a big mountain of clay. A trace is like taking a knife and just slicing straight down. You're basically fixing one of your variables so you can see what happens with the other one. And here's exactly how it works. By deciding to hold y at a constant value, we've essentially sliced our surface vertically. Now look at the edge of that cut, that highlighted curve. What is it? It's a simple 2D curve. Just like that, we've turned a complex 3D problem into a familiar 2D one that we already know how to handle. So, traces are awesome for vertical slices. But what if we want a bird's eye view? Well, for that, we can use an idea that you've probably already seen, even if you didn't realize you were looking at math. This is a topographical map. Hikers use them all the time to understand the shape of the land. Every single line on this map connects points that are at the exact same elevation, the exact same height. It's a flat 2D picture of a 3D landscape. And here's the secret to reading it. When you see those lines packed really tight together, it means the elevation is changing super fast. That's a steep cliff. But when the lines are spread way far apart, the elevation is barely changing at all. That's a gentle slope or maybe a nice flat plateau. So in math, we call these lines level curves or contours. All they are is just a collection of all the x, y input pairs that give you the exact same z value. It's literally the same thing as taking a horizontal slice of our surface at one specific height. And boom, here's where it all clicks. Look at this. On the left, you've got the 2D contour map. On the right, you've got the 3D surface that it represents. Each one of those blue ovals on the map corresponds perfectly to a horizontal slice of the 3D shape. It's like the map is the blueprint, the DNA for the entire landscape. All right, so now that we know how to read these maps, let's see them in action. A whole new gallery of shapes is about to open up. Let's take a quick tour. First up, a classic, the paraboloid. It's a perfect bowl shape. And its contour map, a beautiful set of evenly spaced concentric circles. That tells you that as you move away from the center, the height increases at a very steady, predictable rate, creating that smooth curve. Now check these two out. On the top, a cone. Its map is also circles, but notice how they get closer and closer together? That tells you the slope is getting steeper and steeper. Then below it, we have this wild saddle shape. Its map isn't circles at all. It's these intersecting curves. Two totally different shapes, two completely unique 2D fingerprints. And what's really amazing is that this technique works even for super complex surfaces, like this wavy kind of egg carton shape. I mean, the contour map might look a little crazy at first glance, but all the information is there. All the peaks, all the valleys, all the slopes, laid out neatly on a simple 2D grid. It turns chaos into something we can actually read and understand. You see, what we've really done here is we've unlocked a whole new way of seeing. Once you can read that 2D contour map, you can understand and explore entire three-dimensional worlds without ever having to draw them. So the real question is, what new landscapes are you going to discover?